Thanks. Thank you, Julia. Thanks to all the organizers. And thank you all for being here for 2 weeks now, going on 3. So I don't know if I'm going to tell you a lot of all the detail that you want. But let me start with asking you a question. How many of you know what Technicolor is? Not Technicolor in particle physics. Ah, okay. We still have a few. Okay. So I like film. And old films used to have, some of them, very vibrant colors. And that was the result of a process called Technicolor. So essentially what they did is had these special cameras and they used different lenses in different colors. And then they superimposed them and you got these very colorful, vibrant pictures. So think about like if you have seen musicals from the 30s to the 50s, really popping up. And the key idea here is that each one of the colors is bringing a different piece of information about the real image. And that is more or less how I would like you to think about multi-messenger physics. Now, the reality of the universe is that we can see it using multiple wavelengths of light, but also different things that are not light. So the goal here is that if we have a source of high energy neutrinos, cosmic rays, or whatever, then we use each one of the messengers that we get our hands on to learn more and more about the sources. So you combine optical observations, infrared observations, and then at the highest energy range, X-rays and gamma rays, and then neutrinos, then the superposition of those will give you what the real physical image should be. And if you want to continue the analogy with film, if you add gravitational waves, you get the music. So what I will do today is, and over the next few lectures, is a bit of everything. So there's a bit of theory, and there's a bit of connection to experiment, which is something I like. I'm a theorist, but I'm really connected to actually building the things as well, and a bit of history. And in doing so, I will tell you about the music and some of the lyrics. And by that, I mean I'll tell you details, but I'll also leave some details out, and we can talk about that. Okay, so now I'll be switching between board and screen. I'm being told I need to go here for a moment to turn that off, so excuse me. To turn that off. No, the screen. Yeah. So give me a moment. There we go. Okay, so let's see. So the fundamental reason, let me start with the big picture. The fundamental reason why we think that cosmic rays, electromagnetic waves, and neutrinos, which are the 3 messengers that I'm going to be talking about, might be made in the same processes, comes from a very simple toy model consideration. And that is that if we have a source of astrophysical cosmic rays, and by that, and this will become later more clear, but by that I mean a compact source where you can accelerate protons to very high energies, then you have them lying around. Typically these are not in vacuum, so there is some radiation fields or some other matter around. Let me just write some interaction with a photon. Those photons themselves could have been emitted by synchrotron radiation of electrons or protons themselves, and that will give you this couple of processes. So protons plus neutral pions, and that happens about actually 2/3 of the time, so the branching ratio is 2/3. Or you could also have neutrons plus pi pluses, charged pions, and that happens the other 1/3 of the time. Is that the only process by which protons and photons can interact? No, but this is what we're going to use for now as our toy model. And these protons typically are living in a source that is, as I said, able to accelerate them up to very high energies, and by that I mean 10 to the 20 electron volts or so at most. And so if you now will have in a source something like looks like this. The number density of protons is a falling function of their energy. Typically, it is some power of the energy, -2 or more. Whereas these photons typically have a bit more structure in their spectrum. So this is now number density of photons, and this is energy of the photons, and this is something maybe like this. Some kink in an otherwise featureless energy spectrum, and that kink can be due to any number of reasons. It could be due to the source itself making primarily photons of a certain energy. And again, this will all become clearer later. The key aspect of this is the following. These pi zeros promptly decay into gamma rays, and those gamma rays we sometimes are able to detect from a particular source. That is not the only source of gamma rays. You can make also gamma rays by the synchrotron emission of electrons, for instance. But there is certainly a hadronic origin to the gamma rays, and that will become important later. And also, the pi pluses will decay into one muon, and then a new mu neutrino, and this muon itself will decay into one muon anti-mu neutrino, one electron neutrino, one positron. So, and there's one more thing here. That neutron over here will beta decay and gives us protons and electrons and a neutrino as well. So, what are we getting out of the same network of processes? We're getting gamma rays, we're getting neutrinos, we're getting electrons as well, and we're getting protons. So those are the cosmic rays, the protons. The energy of these particles is connected. So the energy of the photons, for instance, is roughly 1/10 of the energy of the parent proton that gave rise to the whole process, and the energy of the neutrino is roughly 1/20 of that. So if you see, I work primarily in neutrinos. If you see neutrinos of 1 PeV, then chances are they were made by a proton of 20 PeV or so. And when I say PeV, and I'm going to write it over here because I know that I take it for granted, I mean 10 to the 15 electron volts. Okay? And when I say TeV, I meant, you probably know this, just let me put it here. And when I say, okay, I'm going to take it to the extreme. EeV means 10 to the 18 electron volts. Okay, we'll keep it over there. So, multi-messenger astrophysics is based on these kind of relations between the different messengers. The fact that we see protons, neutrinos, or gamma rays by themselves gives us a lot of information. When we put them all together and do some model building, we learn more. So there's many places here where I can start pulling the thread of explaining things, but I want to start from the cosmic rays. These guys over here. Before that, there's one extra motivation that I want to give you, and that is an observational one. So this is more or less theory. Essentially, every time you have a collection of protons and a collection of photons in a compact enough environment, you will have this kind of process. But that is no guarantee that they actually are happening in whatever astrophysical conditions are out there. However, there is an observational piece of evidence here, and that is pretty recent. Let me plot here energy, and this will be energy of the particles that I'm going to plot here. And let me put here energy flux, and I'll say what that means in a moment. Energy flux. Actually, let me actually write the units as well. So it's GeV per centimeter square per second per steradian. So this means this is a diffuse flux of particles. That's why I'm writing steradian. This is the unit of solid angle. So I'm looking at the sky and I'm assuming the the flux neutrinos, cosmic rays, and photons is isotropic. So we've been looking at gamma rays, which we call photons, above MeV energies for decades, so we're pretty good at measuring them. And if we start here at, let me be clear with the units, this is electron volts. So this is 10 to the 9, this is 10 to the 20, 11 orders of magnitude. There's more or less a division in three parts. And you get the photons here, then the flux is, let me see if I can draw this correctly. This is 10 to the minus 10, this is 10 to the minus 4, and somewhere around here is what I'm going to put the 10 to the minus, what is this? No, 8. Okay, so the flux that we see is more or less a falling power law. There's many detectors that actually look at gamma rays, so there's multiple points over here. On the other end are the cosmic rays, and by that I mean not only the protons that I wrote here, but essentially any nuclei that is able to leave an astrophysical source with energies that reach up to these very, very high energies. And again, we've been seeing cosmic rays for decades at this point, and their flux is also a falling function of their energy. And the third piece of the argument is pretty new, and that is neutrinos. So whereas these reaches about 10 to the 12, so 1 TeV, and these cosmic rays, at least the extragalactic ones, as I will show later, start at around 10 to the 17 electron volts. Neutrinos fall somewhere in the middle, at least the ones we have seen so far. And unsurprisingly, or maybe surprisingly, their energy is also, or their spectrum is also a falling function of the energy. So the key observation here, which we hoped for but we didn't know until about 10 years ago when we discovered these neutrinos, is that the energy flux of these three particles is at around the same level. What does that mean? Maybe it's a coincidence, and maybe these and these are being made by three different completely unrelated astrophysical processes, or maybe nature is a bit kinder and actually they are being made in processes like that are linked together, and what we're seeing is evidence of that. So we're getting equal amount of energy in each one of the three messengers. So that is essentially the motivation why multi-messenger astrophysics is not just interesting from theory, but is interesting from experiment. All right. So I said I was gonna put in some history here, and that is something that I think it's good to put our work in context. So let me move the third here. Okay, I'm going to use it soon. So history. And when I say history, I mean I'm just going to be very, very biased and just mention the dates I'm interested in. So let's start very early. 1896, radioactivity is discovered. So that's radium and uranium, yeah. And that's Becquerel and Pierre Curie and Marie Curie. So why is this important? We'll see in a moment. And then in 1911, cosmic rays are discovered. Not at the very highest energies that I've drawn over there, but actually at energies that are around here, which I haven't drawn in this picture. So this is the first indications for cosmic rays. And this itself has an interesting history that I'm going to talk about in a moment. Okay, because I like neutrinos, neutrinos are proposed, but not discovered. Proposed. That would take another 26 years. And then neutrinos are discovered. So I was telling a bit of this history some time ago to an undergrad student of mine, and when I got to this point, I was explaining how this experiment was run and how the neutrinos were discovered, which is an interesting history. She said, "Were you alive back then?" Which made me feel some sort of way. I was not alive back then. Okay, so there we go. 1961, the first gamma ray sources are found, I'm writing this because I want you to really. First gamma ray source is found. I want to really know that this is a decades-long field. But it's, astrophysical sources. And then, let's go a bit faster. So 62, ultra high energy, UHE, cosmic rays are discovered. And by that, now I do mean the cosmic rays that I drew here. So 10 to the 17 electron volts and above. Just to put this in context, this is roughly the kinetic energy of a flying mosquito. Over here is the kinetic energy of a kicked football in one proton. So you've heard that analogy before. So this is 1962 in the volcano. This is not very well known for some reason, but in the Volcano Ranch experiment, ultra high energy cosmic rays, were discovered for the first time. And then, we learn a lot about these, and I'm skipping a lot. And in 2013, now I was alive then, and in 2013, IceCube discovers high energy neutrinos. High energy neutrinos. And by high energies, I mean above maybe 10 TeV or so. Very well. And then, from then to now, what we have been doing is finding sources of high energy neutrinos. And I'm skipping a lot. So I'm going to come back to these at the very end, and I'll show you some news. But in the meantime, of course, all of these fields have been evolving in time. We have actually mapped the cosmic ray spectrum much better than when we first saw them in 1911. And we know many more gamma ray sources than we knew in 1961. In fact, just 3 or 4 years ago, we found the first gamma ray astrophysical source that reaches up to PeV energies, 10 to the 15 electron volts. Okay, now, the last bit about history is connected to this. And I said I was going to start pulling the thread of multi-messenger physics, starting with the cosmic rays. And the reason is because I think it's a natural progression of how we got to where we are. So put yourself in 1896. The radioactivity is discovered, and then we start finding out that the ground has radioactive elements, and then there is a base level of radioactivity everywhere, and it changes, of course, where you go, but there's always non-zero. So at the beginning of the 20th century, there's 2 facts, and cosmic rays discovered. And the first fact is that, 1, there's ambient radioactivity. And 2, and this is the belief at the time, it comes, I'm going to say, solely from the ground. So from radioactive elements in the ground, in the crust. And that is not a bad assumption. If you can move your back then, your electrometer, your Geiger counter now around, then you will find that if you climb a mountain, you will have your base level of reactivity go down the further up you go. And the reason is, people only climbed with equipment mountains up to 1 kilometer high. But then, so they actually saw more reactivity here than here. And it doesn't matter right now. Let me be a bit vague and not put units here. So there's more here and less here. And this was the state of the art until 1911, when this completely mad physicist called Victor Hess climbed into balloons and climbed up to 5 kilometers during storms and took with him an electrometer, which is what he used to measure ionization of the air due to particles going through it, which is a measure of charge. So what he found when he repeated the measurement is altitude, and I'm gonna put here ions per second. So number of clicks in your Geiger counter today per second. What he found was that 2, 3, 4, 5, 6. By the way, climbing up to 5 kilometers today in a balloon is still dangerous. So imagine that 100 years ago. 10, 20, 30. 10, 20, and 30. This is in kilometers, by the way. Okay, so as I said, people typically have made these measurements up to 1 kilometer in height, and then indeed the number goes down and then it goes up to where he could get. So evidently not all radioactivity comes from the ground, and he said, quote, well, translated quote, he detected an unknown penetrating radiation. And today we call that cosmic rays. He got a Nobel Prize for that in 1936. So today we know that what he was seeing was protons and other nuclei that are coming from outside the Earth and that reach, eventually we will discover, up to the highest energies we can see so far. So everything else from my personal bias perspective follows from that. In fact, maybe you already know a bit of the story, but antimatter and some of the first mesons were discovered in cosmic ray showers. So there's also a very, very deep link between particle physics and astrophysics from that perspective. Now, this is what I'm looking for. Okay, so today we know the cosmic ray spectrum pretty well over about 12 orders of magnitude in energy and several orders of magnitude in flux. And let me just make a cartoon sketch of how it looks. And it looks like, let me actually do it in log scale because that's easier for me to draw. Log of energy in GeV, and this is flux of cosmic rays, typically represented by phi, multiplied by power 2.6 of the cosmic ray energy. And 2.6 makes sense here because this guy over here, turns out it is like e to the minus 2.6. So when you multiply by 2.6, it flattens out the spectrum and it's easy to see changes in the spectrum with energy. So the units are similar to what I drew before, except now you have a actually a 1.6 here, 1.6 centimeter square per second per steradian. So number of particles that reaches the surface of the Earth per unit energy, per unit area, per unit second, per unit steradian. And let me, this is 11, this is 21. Let's see if I actually make it. 12. 13, 14, 15, 16, 17, 18, 19, 20, that's not so bad, okay. 15, 16, 17, 18, 19, 20, and this is about 1, 2, 3, 4. Okay. So the LHC in terms of energies is around here, a bit higher. Sorry, I got it wrong, 13. The LHC is about here, now it's okay. This is the flying mosquito that I was talking about before. So this is as high as we can go today with our particle accelerators, and possibly in the near future we cannot go much, much higher. So the flux looks kind of like this. Let me see if I can draw it. It has one kink here, it has another kink here, and another kink here. Something like this. So it's not quite a power law, it's a power law with kinks. And this has been measured, I'm just doing a cartoon picture of this. When we are at energies roughly below, I'm going to say 10 to the 14, you can actually measure the cosmic rays directly. So you can be like Hess and put your detector up there in a balloon or in the International Space Station and measure it. So direct measures. And that is because measurements, and that is because the flux is quite high. So even if you have a small detector, the number of particles that impact on it is enough to make a measurement within a reasonable amount of time. But then as you see, the flux quickly falls. And every measurement of the cosmic ray spectrum above energies of PeV or so, I'm just being a bit hazy here, are indirect. And what you do is rather look at the products of the particle showers that the cosmic rays initiate in the atmosphere, or sometimes even inside medium like ice. So there's a few features in this spectrum, and I'll come back to them later. Right now I'm just laying the groundwork for this. There's at roughly a few PeV, 3 PeV actually, the knee. There is the second knee, yeah. So this is an alien leg, and this is the ankle. And at the very, very high energies is what we call the GCK cutoff. We'll come back to this. The main takeaway from here is that each one of these features signals a transition of some sort. The knee apparently signals a transition between when the protons are coming from the Milky Way primarily to when the protons are coming from outside the Milky Way primarily. The second knee is the same, but for the iron nuclei in the cosmic ray spectrum. The ankle might signal something else, I'll come to that later. And the GCK cutoff, that is connected to the interaction of ultra-high energy cosmic rays with the cosmological photon background as they propagate to Earth. And this is a suppression at the very, very high energies. And this is signaling that the universe is not transparent to cosmic rays. It is also not transparent to photons as well. Okay, so this is the big picture. And I'm going to start getting into more detail, but before that, I always find it useful to ask and answer a few big picture questions. So I don't need to write this. So cosmic rays, what are they? Especially at the highest energies. They are nuclei that get accelerated, presumably by some astrophysical phenomenon that has the capacity to trap them in some magnetic field and take them slowly but surely to very, very high energies. We don't know exactly what those sources are, and that's why I'm being so vague about it. But we'll come later to what the conditions should be in them for them to be cosmic accelerators. So is 10 to the 17 electron volts and above a lot? Yes, it is a lot. Those are the highest energies that we have seen so far. They're roughly 10 to the 5 to 10 to the 8 times higher than the protons at the LHC. I had a comparison here. Yes, that's what I said earlier. A 10 to a 20 electron volt proton has the kinetic energy of a kicked football. Okay. I said, what is making them? This is a question that we have been asking ourselves for decades at this point, and the answer is anything that can get protons and photons together in a compact enough region and accelerate the protons to very high energies, or anything that can get protons to interact with the environment also after accelerating them to very high energies. And that can include things like especially luminous supernovae. They can include active supermassive black holes, or even the magnetospheres of newborn pulsars. So there's a few things that we'll come back to later, and I'll show you roughly how they do. But in general, they are just exotic non-thermal accelerators. And by non-thermal, I mean you just don't get to these energies by heating things up and that medium emitting. You need to do something else. And that something else, we'll come to it, is called collisionless acceleration. Why is it so hard to find the sources of cosmic rays? There's two reasons. First, these are charged particles and the universe is magnetized. So there is an extragalactic magnetic field. There's a galactic magnetic field inside the Milky Way. And any particle traveling in a magnetic field will deflect. So if you see a cosmic ray coming from that direction, it has already been deflected by who knows how many degrees from its original emission direction. So if you look at the direction, you won't find the source of that cosmic ray. Statistically, if you had millions of cosmic rays distributed around across the sky, then yes, some will be accumulated more in the directions where the sources lie than where they don't lie. We are not there yet. Especially the highest energies where we only have about 20 ultra-high energy cosmic rays. Yeah. And the second reason is the ultra-high energy cosmic rays at the highest energies are rare. And that is connected to what I said earlier. There is a non-transparency of the universe to the very high energy cosmic rays. So we don't get to see them. They don't reach Earth. So we're working with, at the very high energies, low statistics and very adverse conditions. And that is why we don't know what the sources are. And by translation, we also don't know what the sources are of the most energetic photons and the most energetic neutrinos, assuming they're all made in the same sources. Okay. Let's now look at the big picture, and then we'll start zoning into the rest. Let's draw it here. By the way, please feel free to interrupt me at any point. And if you're starved for math, it will come. So I'm just being nice. So let's talk about the big picture. The big picture is we're sitting here in the Milky Way. And actually we're like one of the outer parts of one of the arms. And then there is a collection of astrophysical sources that are serving as cosmic accelerators, and they're distributed in redshift with some distribution. So there are some sources, there are more sources at some redshifts than at others, and that is a result of the normal evolution of matter across cosmological scales. So if we are at the very local universe, so z of 0.01, that is roughly 100 megaparsecs. If we're at z of, let me see if I put this correctly. Yes, z of 1, we are at a few gigaparsecs of distance from us. Turns out that most of the sources that could be candidate ultra-high energy cosmic ray sources lie around z of 1. Because most of the star formation happen at z of 1. That is a tracer of the matter concentration in the universe. So these sources are distributed at different redshifts, and they will emit cosmic rays. And as I said, the cosmic rays will bend, and eventually they will, some of them reach us, but by the time they have reached us, they have already been diffusing a very long time. Two things happen when the cosmic rays are propagating. And the first one is, I'm going to draw it like a little explosion here. So this is a proton. The first thing that happens here is that if a proton interacts with a photon from the cosmic microwave background or some other cosmological photon background, I'll come back to proper Feynman diagrams later, it can lose energy by pair production. So you still get a proton at the end, but that proton is lower energy than the original one. So they lose energy by pair production as they propagate. And the second thing that can happen is that as they are traveling, let me draw it here, they can also have an inelastic interaction, again, with one of the cosmological photons over there. But in this case, let me draw it like this, proton. What you get out is rather, you destroy the proton and then you get a neutrino out of here. We call these cosmogenic neutrinos because they are born, I guess, in the cosmos, which, come to think of it, everything is. So I'm not sure it's a good name, but they're called cosmogenic neutrinos. So just to get an idea of this, I was talking about magnetic fields earlier. The extragalactic magnetic fields, we believe, are of nano-Gauss scale. We don't really know, but those are best guesses. And in the Milky Way, they are of order of micro-Gauss. And as a comparison, the geomagnetic field is between 0.25 and 0.65 Gauss. So these are truly small magnetic fields, but these particles are propagating over cosmological scale distances, so the deflections are actually significant, and we'll show them later. Now, this is the first time I'm showing production of neutrinos in a setting, and the interesting thing here is that once they are made, they will travel in a straight line. So if we happen to be in the path of this, then we will see it. And of course, because these neutrinos are being produced by all cosmic rays, and the cosmic rays have diffused by the time they produce them, we actually do see a flux of neutrinos at the Earth, or we hope to see, as we will see. We will find out later. We haven't actually detected those cosmogenic neutrinos, not at these energies. Okay, so that's the big picture. Now, this also tells us how I will present things. So the first part will be production. Yeah. And that is, how do we make cosmic rays at the sources? And later, how we make gamma rays and neutrinos at the sources. The second one is propagation. And the third one is detection. Okay, and this is how we see cosmic rays, mainly cosmic rays and neutrinos in the Earth, at the Earth. Okay. Is there any questions so far? Good. Then let's start with production. And by production, I mean acceleration. So as I said, we need a mechanism that allows us to reach, for cosmic rays, energies of up to 10 to the 20 electron volts or so, which are the energies we have actually detected, at least some of the cosmic rays. So the key thing here is that every acceleration process, every cosmic ray acceleration process is electromagnetic in nature. And the second key thing here is that you need electric fields in order to accelerate charged particles. Magnetic fields are not enough. If you remember your electromagnetism classes, magnetic field doesn't do work on particles. But then there is a bit of an issue, and the issue is the following. When we are in an accelerator like the LHC, I'm going to put it here, human-made accelerators and natural accelerators. See, the conditions are quite different. So when we're in a human-made accelerator, we have very ordered field lines and very, say, well-planned so that we can accelerate our particles up to the energies that we want to reach. Astrophysical accelerators are not like that. They are messy, and typically they are like shock waves of matter moving in some direction with some very high speed. And as you will say, as I will show in a moment, there are particles that are crossing these shocks multiple times, and each time they cross the shocks, they get a little bit of an energy boost. And at the end, we reach the highest energies we want. So the acceleration in this case occurs in vacuum. I mean, inside the tubes in the LHC, there's a very, very high vacuum, whereas here it occurs in a medium. The electromagnetic fields here are regular or ordered, regular. And then here they're messy, as I said. And the beam dumps, so where you're actually allowing your particles to interact, these are precisely regulated. So we have a few interaction points along the accelerator, and we build the detectors around those interaction points, precisely regulated. Whereas here, they're fully unregulated. So particles are just constantly interacting all the time, everywhere. Which is good for us, because every time a proton is interacting, as I showed at the beginning, you get photons and neutrinos out of it. And that's also part of the picture. Okay, so I actually think there is one interesting piece of information that typically does not get very much attention, and that is that even though we're going to be talking about this and how you can accelerate things in a messy environment by a process called stochastic acceleration, and we'll come back to that later, there's also regular acceleration. So there is an important difference there because well, not because. There's an important difference, but it turns out that under some conditions, maybe nature is not as messy. And I'll just want to make a little parenthesis here and show what that means. So I'm going to call this regular acceleration, and that will be a bit closer to what we typically think when we're accelerating particles. And I'm going to call here stochastic acceleration, which is the one that is applies more to the astrophysical environments we'll be talking about. So the difference here is that there is a large-scale electric field here. So sustained over long distances, that's what I mean, that is able to boost particles to high energy. So the mean value of the magnetic field is non-zero over a long distance, whereas here there is only small-scale electric fields, but they are embedded in turbulent matter. So there is no long coherence in these fields, but there is variation at small scales. So there's a standard deviation on top of the regular component of the electric field, and that is what actually will take care of the acceleration. And we will see after I write this that this leads to Fermi acceleration, whereas in the regular case, this only happens under special conditions. How in a messy environment can you keep a magnetic field unperturbed over long distances, at least long enough to accelerate particles to high energies? You need special configurations, needs special circumstances. And there's a couple of special circumstances here, and one of them you might actually have seen before. So there's two examples that I like, and the first one, let me make a distinction here. The first one is called unipolar inductor, which is a very cool name. Inductor. So what this is you have a rotating magnetic field, and that happens in nature in like a pulsar, for instance, in the magnetosphere of a pulsar. But it happens in your physics labs also in the Faraday wheels you might have seen at some point. So you have a wheel. Typically, this is a wheel with a lever arm, and then you can crank the lever arm, and it has some magnetic field. I'm gonna draw here. I wanna get this correct. So the electrons inside, will experience a Lorentz force. Of course, they're being moved. If this is being rotated in this direction, they're being also moved in the same direction. But there's a centripetal force, and there's a Lorentz force. So there's a Lorentz force. All of them are feeling it. And if you put you measure the voltage between, say, the center of the wheel and the surface of the wheel, then this is non-zero when you are moving the wheel. And remember, by Lorentz force, I mean this, right? Okay, so something like this happens in environments like a rotating pulsar, and the surface. One of the points where you're measuring the voltage is the magnetosphere, or actually the surface of the pulsar, and then the other point is at infinity. And then if you were to put a voltmeter between the surface and infinity, there's a voltage. So you can actually extract work from such a configuration that looks like a Faraday wheel in astrophysics. And the second one is called magnetic reconnection. And that, you might have seen these NASA Solar Observer videos, because this happens in the sun, the surface of the sun. So when you have magnetic fields of two different orientations in two different regions coming together, the lines will sometimes merge back, and that merging back creates an electric field over the region where they're being merged. So just to, without going into a lot of detail, just to show you how it looks. So we have magnetic field lines that go like this. Let me complete this here. And this is moving in this direction, and this is moving this direction. Then I'm gonna write here before and after. When they're close together, what will happen is they will merge, and something like this. So now this is in this direction, and now this is in this direction. And when this happens, you create a magnetic field, an electric field with an intensity that is of the order of the size where this merging happens, L times the magnetic field strength of the field that is actually being merged. So as you can imagine, those kind of configurations, either the unipolar inductor or the magnetic reconnection, need special circumstances, and in most astrophysical environments, things are too messy for those to happen. What happens in astrophysical environments is what I wrote there, Fermi acceleration, and that goes back to 1941 by none other than Enrico Fermi. So Enrico Fermi proposed the original mechanism of Fermi acceleration, which today is known as second order Fermi acceleration. And you will see why it's called second order. Partially it's because it's not as good as first order, but there's another reason. Where is it? Okay. So now we are in the realm, from now on, in the realm of stochastic acceleration. Okay, so his his idea back in 1949, sorry, is that you could have clouds of magnetized matter moving at some speed, some high speed. Let me draw a few. And then you would have charged particles bounce off of the clouds. And every time they bounce off of a cloud, they get a little boost of energy. So they start with some energy and some initial speed. And then every time this bounce happens, then there is a change in the energy that it's positive, so they're gaining energy, and we'll see it happens to be proportional to the square of the speed of the cloud. That's why it's called Fermi, second order Fermi acceleration. So these are, he called them magnetic mirrors. So in the center of mass of this frame, of this interaction, the energy of the particle, of the proton, let's say, is, the momentum, sorry, is unchanged. The energy is unchanged, but its direction is. Okay, so let's write things in the lab frame where things become important. Oh, interesting, sorry. So in the lab frame, this delta E over E, so the change in the energy after one mirror bounce. I will not derive this, but I will point you to where you can do it, is V cloud times V cosmic ray, so the incoming cosmic ray energy, cosine of theta, I'll draw what theta is in a moment, times 2 times V cloud squared. Okay, and theta, just I want to be sure I get it right, is the direction between the incoming cosmic ray and the velocity of the cloud. This is theta. Very well. So, right. So we're here. Right. You want the right-hand side to be positive because you want the particle to be accelerated every time it bounces, and that gives us what the condition should be between these quantities to be positive on average. And theta is presumably a random variable, but let's put ourselves in a position where the clouds are distributed isotropically, and the probability of a collision with some angle theta is p theta proportional to this. So it's proportional to the cloud velocity. This is an ansatz, and we'll see that actually it gives us the result we want. Okay. If you now calculate what the average value of this is, this is average over all possible directions, then let's do it here. 0 to pi, that expression of delta E over E, that expression of probability, and then the element angle here, and then I'm going to normalize it over this because I want the distribution. Okay. In the limit where the cosmic ray velocity is of order of the speed of light in natural units, this is about 8/3 V cloud squared, and you can convince yourself of that by doing the integral. So because this is positive, then on average particles gain energy. So some of them in some collisions will lose, some of them will win, but because the clouds are moving in this direction preferentially, then there is a net gain of energy. Particles gain energy. On average. Okay, so that's a good. This seems to work. We'll see in a moment that it doesn't. That is why we needed the first order term now. So so far what we only have is that the average delta E over E is positive, which is good. But now let's calculate the increase over time of the particle energy, increase in T of the particle energy. And by that I mean dE dt. So if this process continues over time, how much energy will we get? And that is R, and R here will be I wrote it as the proton-cloud interaction rate, or maybe it's better to write cosmic ray cloud interaction rate. So how many interactions happen per unit time, times the average delta E over E that we just derived, times E. And if you plug this in, it turns out it is like this, cloud squared ER. Okay, this is an equation one can solve. So if one does solve the equation, the energy at time t will be some initial energy with which the particles start, and this is an exponential solution. This is 1/3 speed of the cloud R t. Okay, so far so good. So until now, we don't have any reason to believe that there's any problem with that mechanism. Okay. There's, however, one more thing here. Let me bring it to light by writing this. There's a probability in each bounce of the mirror that the particle escapes the system, and then it doesn't get to bounce anymore, and it doesn't get accelerated anymore. So let me call T escape the time scale for the escape of the particle from this region where the magnetic mirrors live. Okay, and so the rate of particle escape, now n is the number of particles, is the initial number over the escape time scale. You can convince yourself of that. Actually, so now we want to find over time what is the steady state of the number of particles in the system at different energies. So for that, steady state solution for the number of accelerated particles. Of a certain energy. So I'm writing this because this will become something that we get back to over and over again later. T, this is a simple transport equation, dE dt and E, and then is the loss term over here. And because we want the steady state solution, we're demanding this to be 0. We want the solution for the number of particles that have been accelerated once the system has reached equilibrium. So if you do the calculation using what we found over there, this is 1/3 V cloud squared RE, again, and E over tau escape. There's one extra step that I'm going to skip. You can do it if you wish. But then the number of particles accelerated up to energy E is proportional to the energy to this power, -1 minus 3/8 1 over the cloud velocity squared r tau scape. Okay. So it's a power law, which is good. Remember when I drew the cosmic ray spectrum, it was a power law with some extra features. Let's forget about the extra features for now. What is the problem with second order Fermi acceleration? The problem is it is, under realistic astrophysical conditions, too slow. So let me put in some numbers. So velocities of clouds in general are typically of 10 to the minus 4 c. And the rate, the interaction rate, is of the size of the inverse of the cross section, let's put it that way, between cosmic rays and photons, which depends also on the density on the photons, sorry, of the clouds. It depends on the density of the clouds inside a region. And it turns out that the size of the region that typically contains this magnetic mirrors, in principle, is like 0.1 parsecs. 1 parsec is like 3 light years. So if we want to find what the interaction rate is 0.1, c over 0.1 parsecs. You plug that in, you can estimate the escape time. Actually, you can define it first, like E dE dt, this is inverse, and that is about 12 mega years, so 12 million years. Okay, what does this mean? It means that even though second order Fermi acceleration may happen, so you might have conditions under which you can bounce off magnetic mirrors, and it will give you a power law in the energy spectrum of the protons as you wished, the time it will take for that to happen is about 12 million years. And that is too long. So we expect that, for instance, inside the Milky Way, particles will escape the Milky Way before they get to 12 million years. And not only that, there's energy loss processes that I have not accounted for here that will make the acceleration slower than what this ideal scenario looks like. So if you're thinking, for instance, about cosmic ray emission from a very short-lived transient event, like a supernova, or even the few months long flares of some supermassive black holes, then 12 million years doesn't work. So the reason fundamentally goes back to the fact that the gain in energy is proportional to the square of the velocity of the magnetic mirrors. And because this is a number in natural units that is smaller than 1, if you square it, it's an even smaller number. We want something that instead grows proportionally to the velocity, not to the velocity squared. And that is first order Fermi acceleration. Let me see how we're doing in time. Oh, we're good. Okay. Are there questions so far? Good. Okay. Then let me do first order Fermi acceleration, and then I'll stop for a little bit. By the way, I said earlier that we cannot do work just with magnetic fields. We need electric fields. So where are we accelerating this part? What energy are we using to accelerate these particles with? Does anyone have an answer to that? Where are we taking energy off? Well, the only place we can take energy off of is the fact that these guys are moving. So we're subtracting kinetic energy from the clouds and giving it to the protons. So we're also slowing them down. But it just doesn't matter. Okay, first order Fermi acceleration, which we will see doesn't have that problem. All right. Okay, let's see. So the geometry of the problem here was we have an isotropic distribution of clouds that are moving preferentially along some direction, and then we have protons or configuration in general bouncing off of them. But there are geometries that are more conducive to particle acceleration, that are more efficient for that. And in the 1970s, that was explored in the form of what came to be known as diffusive shock acceleration. And now this is the preferred mechanism for stochastic particle acceleration in astrophysical environments, even though it has still problems. So instead of having discrete mirrors that we bounce off, the geometry is different. We have some compact emitter for the sake of compact source. For the sake of the illustration here, think about it as a magnetar or even a supermassive black hole in an active galactic nucleus. This is emitting some jet of relativistically moving matter. So this is all moving with some relativistic speed. This is a gamma factor. So we call this a relativistic outflow. You have probably seen pictures of jets being emitted by some active galaxies. This is the same kind of phenomenon I'm talking about. Inside, and also at the border with the medium, there are some regions with higher and lower densities, and that results in shocks being formed in the bulk. And by shocks, I mean regions that have different speeds from the surrounding matter. So eventually, those regions crash into the surrounding matter. And there's a shock front with some very small width compared to the size of the whole system. And it is in the shock front, and in going back and forth through it, that acceleration takes place. So if we have a charged particle here, that's going to be our test particle. So the charged particle will be moving from upstream to downstream in the direction of the relativistic outflow, so outwards radially. But it can also do, as we will see, it can also be coming back and doing this. In fact, it has to do it multiple times, because each time it crosses the shock front, as we will see, it will gain a little boost. Okay, so let's talk about things in the lab frame again. In the lab frame, most of the collisions happen, or most of the crosses happen head-on. So now the angle is between the velocity of the particle and the velocity of the outgoing outflow. So if we have a particle that is, say, slightly inclined, this is our theta. And now, because most of the matter is moving in the same direction, then the collisions will typically be between, I should do it like this, yeah. So it will be mostly in the same direction as the outgoing outflow. So one way to parameterize that is to say that the distribution, again, of the collision angles is now proportional to cosine of theta. Before, we had assumed a different shape over there, that depending on the speed of the cloud. Here, there's no such a thing. And again, this is just an ansatz. We put it here because it works. You can actually do simulations, and you don't have to rely on such an assumption. And it still works. So we calculate, again, the delta E over E on average, so how much energy is gained or lost in an average collision. We go through the same process, but now our integral is like this. I'm putting a hard cut at pi halves. With our new p theta, Same element here. And I'm going to normalize it like before. Okay. If you replace this and do the integral and assume, actually you don't have to assume much here. Well, you do the whole thing, you find 4/3 velocity of the shock. And the velocity of the shock is here. So where does V shock enter in this calculation? I am using the same expression that I used before because it still applies, but I'm changing V cloud for V shock. The kinematics is the same. The geometry is different. Okay, so no longer do we have a square dependence. Now we have a proportional dependence on the velocity of the moving object that is the one that is providing the acceleration, or the kinetic energy to do the acceleration. So this is more efficient, right? This is still a number between 0 and 1, but now, because it's not squared, it's bigger than in the previous case. So what happens here is, as I said, as I drew earlier, you will have this particle going back and forth multiple times through the shock, and each time it will get a little bit of a kick, and eventually on average it will get that much. Okay, so if you want to repeat the calculation, we need to take into account one more thing, because particles can still escape that region, and then they would end up not being accelerated anymore, like it happened in second order Fermi acceleration. So let's consider that. So the probability, let me write it as this, probability that the particle stays in the acceleration region after one shock crossing. Region. Okay, this is, I'm going to put it P. Escape. And I'm going to say that this is roughly 1 minus U. And U is the velocity of the shock, but now relative to the medium. So before when I wrote V shock, that was in our own frame relative to us. Now I'm saying what is the extra speed that it has relative to the fact that it's moving in a medium with its own speed. That is U. All right, so we can write the same kind of equation we wrote earlier to find the steady state solution for the number of particles accelerated. Dn dt. I'm going to skip a few parts here, but it's going to end up looking like minus 4/3 V shock R. This is the same R that I had earlier. E minus N. Let me write it in a second. Here, minus NE RU, and this NERU is coming from this term here. It's coming from here. The escape time scale is 1 over R. Again, you can convince yourself of this. 1 over R times the escape probability, so 1 minus P. And this is R times U, according to what we wrote here. Oops. Escape. So if you demand the steady state solution, this is when this is 0. And again, if you solve it, you end up having a power law solution in the proton energy. It's -1 minus 3/4 U over V shock. Okay, you can convince yourself by solving that equation. But so far so good. Again, we have a power law, which is what we wanted. Now, in lieu of a full astrophysics lecture on shocks, I will indulge myself here and just say that for most strong shocks, and by strong shock I mean something that has a very high value of V shock, or V rather, there is a relation between the density upstream and downstream of the shock that allows us to write these exponential in a say more astrophysically oriented way. Let me just sketch it here. So again, we have our geometry. We have the shock that I wrote there, and I will call this is moving with a u velocity with respect to the relativistic bulk. This is rho 1 of density. This is rho 2 downstream. So in this edge of the shock, this is still moving with V shock. And because of mass conservation through the shock, you have rho 1 times U equals rho 2 times V shock in the rest frame of the shock. That's how it works. And this is the part where when I'm gonna ask for permission to just write this. So rho 2 over rho 1 is 1 plus R, or 1 minus R. And this is, I have to read this, this is the ratio of specific heat capacities of the gas in the medium. Okay, so what this means is it's a measure of how much energy you can dump into the gas, and its temperature goes up after that. So for monoatomic or ionized gas, this R is 5/3, and so rho 2 over rho 1 is 4, and so U over V2, which is the velocity here but measured in the restaurant of the shock, is 1/4. With that, we have what we wanted. So if you now convert back to the original lab frame, you get 3/4 U. You plug this shock in here, then you get what you wanted. Okay, this is the prototypical prediction of what the spectrum of accelerated cosmic rays should be in first order frame acceleration, and in general in any efficient cosmic ray accelerator. Now, when I drew the cartoon picture of the cosmic ray spectrum back when, this was not -2, it was more like -2.6. So what is the problem? And the first problem is I have completely ignored energy losses here. Other than particles escaping the region and not being accelerated anymore, there's no interactions that will dump the energy before they get accelerated. That's one thing. Those interactions will make this steeper. And the second is I'm talking about all the time about idealized conditions. So in practice, this is not exactly proportional to the velocity of the shock. There are some inefficiencies along the way. The reality of things is that even if you plug this into a computer simulation and do actual particle dynamics, you don't really get minus 2.6 as you observe in the spectra. And that just speaks to the difficulty, one of the big problems of astrophysics today, which is we don't know how to accelerate particles up to very, very high energies in relativistic shocks. Certainly something is doing it. This is the best bet. We can actually make it steeper, like minus 2 point something, but we cannot quite get to minus 2.6. And that is ongoing work. But at the core of those arguments lie the fact that the most efficient acceleration process we have is the one where we have a relativistic outflow and the particles are crossing back and forth many times the shocks in them. Okay, I will make a pause now, but before, is there any question? There is.
Is that 1 minus r or
This is a very badly drawn one. And so is this one, sorry. What? Sorry?
R is 5 so how is it positive?
So I don't think I'm getting the question.
When you put the value of r which is more than 1, how's the ratio 4?
When I put the r smaller than 1?
More than 1, it's like r is 5 by 3, right?
Here.
Yeah, when you put it above, you get rho 2 by rho 1, which is more than, which is a positive number.
I don't think okay. You mean if I plug it here, I might have made a mistake. Let's see. Row 2, row 1, 4, U2, 1/4. You're right. I might have made a mistake somewhere in my notes. I probably have a sign change somewhere. I will check. Thank you for noting that. Yeah. But this doesn't change the end result, by the way. Typo. Okay, I see no more questions. So how about we stop for like, 3 minutes? What?
You only have 5 minutes left.
Oh, sorry. So I went too slow. Okay. Then let's stop here anyway, and I'll take questions, and then next lecture I'll say more.